Hi everyone, and welcome to Module 4. In this week's lesson, we're going to discuss standardized scores, in specific the z-score. We will then use z-scores to find the probability of obtaining a given sample from some population. Also, we're going to introduce our first inferential statistical test. These tests will show you how to use a sample mean to make a statement about a population mean. To begin this module, I want to point out that we are currently working with two distributions for any variable. The first is the distribution of the population of interest. The second is the distribution of a sample drawn from this population. We discussed this a bit in Module 1. Recall that we talk about the population distribution in terms of parameters and the sample distribution in terms of sample statistics. These distributions may be very different from one another, especially when the sample is small. This was called the sampling error. The distribution of a population tends to be clustered around the mean, while the distribution of a sample is often much more spread out from the mean. The first thing we are going to discuss this module is the idea of standardizing scores. A standardized score is simply a variable that has been transformed to have a new mean and standard deviation. One of the most common standardized scores that you've probably seen are intelligence quotient scores, or IQ scores. Intelligence scores come from tests that have been standardized to have a mean of 100 and a standard deviation of 15. Standardized scores are very useful when comparing variables that are measured on different scales. As a simple example, suppose we want to figure out whether someone who is 70 inches tall is taller than someone who is 178 centimeters tall. Standardized scores would place both their heights on the same scale to allow us to make that comparison. In statistics, the most common standardized distribution is the z-score. The z-score transforms a variable so that it has a mean of 0 and a standard deviation of 1. The z-score tells us a couple of things. First, negative z-scores indicate that an individual is below the mean, and a positive z-score indicates an individual is above the mean. Second, it is very rare to see z-scores above positive 2 or below negative 2. Z-scores that fall outside of this range may indicate an extreme value. Finally, and this is not obvious yet, the z-scores is one of the cornerstones of inferential statistics. We will cover this in later slides. The formula for a z-score is simple. It is simply an individual score minus the mean divided by the standard deviation. If IQ scores have a mean of 100 and a standard deviation of 15, what is the z-score for an individual who has an IQ of 30? Plugging into our formula, we subtract the mean of 100 from the individual observation of 130 and divide by the standard deviation of 15. We find this equals a z-score of 2, so this person is right on the cusp of having an extremely high IQ. In order to understand why you should want to learn how to calculate and use z-scores, let's talk about a quick example. In the Summer Olympic Games, there are many track and field events, one of which measures not just the speed of an athlete, but also the overall fitness and performance. This is the women's heptathlon. The heptathlon consists of 7 different events, 3 different running races, 2 that measure jumping ability, and 2 that measure throwing ability. The running races are measured in time to completion, whereas the jumping and throwing events are measured in meters or distance. Each event has an individual winner, but how do we determine the overall winner? Should the winner of the long jump be awarded more points than the winner of the shot put? How can you decide who gets crowned with a gold medal when the events of the heptathlon aren't even measured in the same units? This is where the z-score and standard deviation comes into play. It is a way of allowing you to compare values of all sorts of things, whether or not they are measured on the same scale. Let's take a look at calculating z-scores for the women's heptathlon. We want to look at 2 different events and see how we can standardize them so that we can figure out who is the winner of both events combined. After looking up the results of the 2008 Olympics women's heptathlon, specifically the results for the 100-meter dash and the shot put, here's what we find. The mean for the 100-meter dash is 13.79 seconds with a variance of 0.18 seconds squared and a standard deviation of 0.43 seconds. The shot put has a mean of 13.48 meters and a standard deviation of 1.3 meters. From this quick look at the summary statistics, it looks like the results from the 100-meter dash were more closely clustered than those of the shot put. We can tell this by looking at the standard deviation. All of these statistics were calculated in Excel using the statistical functions described in Module 1. Now that we have our descriptive statistics, we can start to answer our question of who did better overall. If we look at the winning results of each event, we can see that Hilaeus Fountain won the 100-meter dash in just 12.78 seconds. Natalia Dobrinska won the shot put by putting the shot 17.29 meters. Now, if we look at each woman's score on the other event, here's our data. Natalia completed the 100-meter dash in 13.44 seconds, good for 6th place overall, and Hilaeus putted the shot 13.36 meters for 18th place overall. If we look at just the place in the rankings of each woman, it would seem like Natalia should score higher overall because in both events her rank seems smaller. What we need to do is to convert the outcomes of both events into the standardized z-scores so that we can compare the two events and determine the overall ranks of the two women. In order to do this, we need to know how to calculate the mean and the standard deviation for each event. We've already used Excel to help us calculate that, so now we can just plug our numbers into the formula. Now to calculate z-scores for each woman for each event, we need to take the result of each woman's performance and subtract out the mean. Then we divide the result by the standard deviation. This gives us the following information for each woman's performance in each event. If we look at the result for the 100-meter dash, a lower score is better, as a lower time means a faster run. The opposite is true for the shot put. A larger score means better results. If we look at the z-score for each event individually, Hilaeus had z-scores greater than 2 below the mean for the 100-meter dash, which is quite a bit considering how short the race is. In the shot put, Natalia had a z-score of almost 3. This still doesn't tell us who the better athlete is. The best way would be able to combine the z-score for both events. In order to combine the results, it might be better to take the absolute value of the z-score for the 100-meter dash before combining it with the shot put. Now we can add up the z-scores for each event and get a total score. For Hilaeus, this gives us a total z-score of 2.24, and for Natalia, a total of 3.75. Now we can say that overall in these two events, Natalia performed best, as her z-score indicates that overall she performed 3.75 standard deviations above the mean when the results for these two events are combined. If we look back at our original hypothesis, we can see that we are able to confirm that Natalia is the better athlete in the combination of these two events. In case you're wondering, Natalia ended up winning the gold, and Hilaeus ended up winning the silver medal in the overall heptathlon. Z-scores have another incredibly important use. They can be used to find the probability of randomly sampling a single value from its population. Going back to the women's 100-meter dash, which had a mean of 13.79 and a standard deviation of 0.43, suppose we want to know the probability of randomly selecting a runner who completed the race in under 13.5 seconds. If we look at the population of if we look at the histogram of the population of runners, we want to know the proportion of runners that fall to the left of the vertical red line. This proportion is called the p-value and corresponds to the probability of randomly sampling a runner who finished the race in under 13.5 seconds. P-values range from 0 to 1 and can be calculated for any variable. P-values closer to 1 indicate that the value we chose is very close to the population mean, while p-values closer to 0 indicate that the value is far away from the population mean. Very small p-values indicate extreme scores. This makes sense because looking at the histogram, we can see the majority of people are gathered around the mean, making them more likely to be sampled than those in the tails. We will use Excel to calculate the p-value, and there is an attached document in Module 4 that demonstrates that. Knowing the probability of randomly sampling a single value is interesting, but not very useful in practice. It is much more useful to know the probability of randomly selecting a sample from a population. This is a topic that trips a lot of students up, so we're going to start with a very small example. Suppose our population contains only 3 members, Paul, Linda, and Julia, who are 65, 70, and 72 inches tall, respectively. This corresponds to a population with a mean of 69. From this population, we want to take samples of 2 of the members, and as a result, 3 possible samples can be drawn. Sample 1 might contain Paul and Linda, sample 2 might contain Paul and Julia, and sample 3 might contain Linda and Julia. These 3 samples have means of 67.5, 68.5, and 71. We can now calculate the probability of randomly sampling any of these sample means. For instance, if we want to know the probability of randomly selecting a sample with a mean that is less than the population mean of 69, we can divide the number of samples with a mean of less than 69 over the total possible number of samples, which is 3 in this case. In our example, 2 of the sample means are less than 69, so we have a 33.3% chance of randomly selecting a sample with a mean of less than the population mean. The collection of all possible sample means of a specific sample size is referred to as a distribution of sample means. When the population size is small, such as in our example, it is simple to calculate the distribution of sample means and find p-values. However, as the population size grows, it becomes more time-consuming and difficult to find every possible sample mean that can possibly be taken from a population. Luckily, we have a set of guidelines that describes the distribution of sample means for any population or sample size. This is called the central limit theorem. The central limit theorem tells us 3 things about the distribution of sample means. The mean of the population of sample means is equal to the overall population mean, mu. The standard deviation of the distribution of sample means is equal to the population standard deviation divided by the square root of the sample size, or sigma divided by the square root of n. This is called the standard error and tells us how spread out the distribution of sample means is. Finally, the distribution of sample means becomes normally distributed as the sample size increases. As a rule of thumb, if the sample size is at least 30, the distribution of sample means will be normal. For the central limit theorem, we can now calculate a z-score for samples. The z-score formula for finding the probability of selecting a random sample is the sample mean minus the population mean divided by the population standard deviation divided by the square root of n. Once we obtain a z-score for a statistic, we can go to Excel to calculate the p-value of randomly drawing that sample from a population. As with before, p-values close to 1 indicate that the sample mean is close to mu, and p-values close to 0 indicate that the sample mean is far away from the population mean. Let's go over an example. Suppose on average, Maymont Hospital admits 30 patients per month with a standard deviation of 5 patients. We want to know the probability that for a 30-day period, Maymont Hospital admits more than 31.5 patients per day on average. We have all the information we need to calculate our z-score. Our sample size is the 30 days, the standard deviation is 5, the population mean is 30, and our sample mean is 31.5. We plug these values into our formula and we obtain a z-score of 1.64. This z-score corresponds to a probability of 0.104. In other words, there's a 10.4% chance that Maymont Hospital will average more than 31.5 patients per day for a given month. Now that we understand z-scores and the central limit theorem, we can finally get to the meat of inferential statistics, hypothesis testing. Hypothesis testing is a procedure for testing questions about data. The basic idea behind hypothesis testing is that we think an effect is happening, and we are going to set criteria for determining if we are correct in our thought. If we meet the criteria, we can conclude that the effect is actually happening, otherwise we cannot. This is where the term inferential statistics comes from. We are using sample means to make inferences about a population. A wide variety of hypotheses exist, but for now we are going to focus on hypothesis tests about means. To begin a hypothesis test, first we have to come up with a hypothesis. A hypothesis is a statement about what we think is actually happening in reality. Going back to the 100-meter Olympics example, a hypothesis might be that athletes from the United States run faster than the average athlete across the world. When we conduct a hypothesis test, we are actually stating two separate hypotheses. The first hypothesis is called the null hypothesis and is written H sub 0. The null hypothesis states that we are wrong. So in our example, the null hypothesis would state that the average American runner is no faster than the average worldwide runner. We would write this H sub O, mu is equal to 13.79, which was overall average time. It is important to note, throughout the process of hypothesis testing, we work under the assumption that the null hypothesis is correct. That is, we assume the value we state in the null hypothesis is the true population mean. The alternative hypothesis, written H sub 1, is our second hypothesis in our research question. In our example, we think that American athletes are faster than the average runner. This would mean that the average U.S. 100-meter time would be different from 13.79. We can write this alternative hypothesis as mu is not equal to 13.79. Once we set our null and alternative hypotheses, we need to determine the criteria for answering our research question. We do this through the use of p-values. Recall that a p-value is the probability of randomly selecting a sample mean from a population. If a p-value is very small, that indicates there's a low probability of randomly sampling a selected mean, if the null hypothesis is true. In our example, U.S. runners really are no different than the average worldwide runner. This is what our null hypothesis says. Then the sample of randomly selected U.S. runners should have a sample mean that is close to the worldwide population mean. This would correspond to a p-value close to 1. On the other hand, if runners from the U.S. really are faster than the rest of the world, their sample mean should be far away from the worldwide population mean, which would correspond to a p-value closer to 0. In order to determine whether our research question is correct, we want to see a sample mean that is a p-value that is very small. This indicates that the probability of drawing the sample mean is so unlikely that the null hypothesis cannot be true. As a rule of thumb, researchers generally decide that p-values less than 0.05 correspond to sample means that are far from the population mean, that the null hypothesis cannot be true. Stated another way, if we find we have a less than 5% chance of randomly drawing a sample mean from the population, then we have evidence that the mean stated in the null hypothesis is false. The third step in hypothesis testing is to collect our statistics and find our p-value. In the present example, that means finding all the information we need to calculate a z-score. Recall, the formula for a z-score for a sample is the sample mean minus the population mean divided by the population standard deviation over the square root of the sample size. So we need 4 pieces of information. The population mean is given in the null hypothesis. In our example, suppose we take a sample of 36 U.S. runners and find a mean 100-meter time of 13.6 seconds. Recall from earlier slides that the population standard deviation was 0.43. We then have enough information to calculate our z-score. We take our sample mean of 13.6 minus the population mean of 13.79 over the standard deviation of 0.43 divided by the square root of our sample size, 36. This gives us a z-score of negative 2.65. When we plug the score into Excel, we obtain a p-value of 0.004. Which brings us to the fourth step, making a decision. We can make 2 decisions in hypothesis testing. If our p-value is less than 0.05, we can reject the null hypothesis. This means the null hypothesis is not true. If our p-value is greater than 0.05, we retain the null hypothesis. This means that we do not have enough evidence to say the null hypothesis is false. Pay attention to the wording of the last sentence, and note that we never say the null hypothesis is true. You could think of this as similar to the outcomes of a criminal trial. A defendant may be judged guilty or non guilty, among other verdicts, but a defendant is never declared as innocent. In our example, we obtain a p-value of 0.004, which is less than 0.05, so we reject the null hypothesis. The final step in hypothesis testing is to explain what our decision in the fourth step actually means. Since we rejected the null hypothesis, that means that we have evidence to suggest that runners from the US are faster than runners worldwide. If we had retained the null hypothesis, that is, if we had a p-value greater than 0.05, we would conclude that we did not see any evidence to suggest US runners are faster than runners worldwide. And that's our first hypothesis test. The procedure we just went over is called a z-test. I know that was a lot of information to process, so I will now go over a couple of examples. One thing that I want you to take away from this is that the process of hypothesis testing will stay the same for every other type of hypothesis test that we do in this course. It'll follow the exact same 5 steps. So, IQ is known to have a population mean of 100 and a standard deviation of 15. A psychiatrist at Maymont Hospital believes her patients are smarter than the general population. She takes a sample of 25 of her patients and finds an average IQ of 103. Is her belief correct? So, step 1, we declare our null and alternative hypotheses. The null hypothesis states her patients are no different than the general population, while the alternative states they are. For the null hypothesis, we say that the population mean is equal to 100. For the alternative hypothesis, we say the population mean is different from 100. Our criterion for this course will always be 0.05. In step 3, we calculate our z-score using the available statistics. We take the sample mean of 103 minus the population mean of 100, divided by the standard deviation of 15 over the sample size of 25. This gives us a z-score of 1 and corresponds to a p-value of 0.159. Since 0.159 is greater than our criteria of 0.05, we retain the null hypothesis. Our psychiatrist is unable to provide evidence that her patients are more intelligent than the general population. Historically, Maymont Hospital has an average patient wait time of 70 minutes with a standard deviation of 10 minutes. A new triage system has been implemented at Maymont, and last month, 64 patients had an average wait time of 65 minutes. Do we have enough evidence to suggest the new triage system significantly decreased wait time? Our null hypothesis states that the triage system had no effect on wait time, while the alternative hypothesis would say there was an effect. This corresponds to the null hypothesis of mu is equal to 70 and an alternative hypothesis of mu not being equal to 70. As always, our criteria is going to be 0.05. In step 3, we calculate the z-score by taking the sample mean of 65 minutes, subtracting the population mean of 70 minutes, dividing by the standard deviation of 10 minutes over the sample size of 64. This gives us a z-score of -4 and corresponds with a p-value of 0.00003. This is less than 0.05, so we reject the null hypothesis and can say we have evidence to suggest the new triage system significantly reduces wait time. And that brings us to the end of Module 4. I again want to point out that in the next 2 modules, we will be dealing with different types of hypothesis tests, and they're all going to follow the same pattern of 5 steps. As long as you get these 5 steps down, I would hope anyways, that being able to calculate these hypothesis tests for different situations will soon become relatively familiar. As always, complete the homework, participate in the discussion board, and email me if you have any questions. Everyone have a good week.